In this module, we will cover three foundational topics that will help you better understand the monitoring modules later in this course. These topics include fortification standards, fortification inputs, and laboratories. We'll start with fortification standards. Standards are published documents which describe the specifications and procedures that industries should follow to manufacture high-quality products that are safe, reliable, and true to the claims on the packaging. Standards are most often prepared at the international level, regional level, and national level. The International Organization for Standardization, better known as ISO, is an example of an entity that prepares international standards. This name will come up again near the end of the course. Regional standards are designed for multiple countries. For instance, the East, Central, and Southern African Health Community, also known as ECSA, creates regional standards to promote health and food safety. In the picture, member countries are shaded in green. Standards for food fortification are almost always designed at the national level by a government agency, such as the Bureau of Standards. For instance, Kenya has a standard for maize and wheat flour fortification. Standards can be voluntary or mandatory. In countries where rice fortification is not mandated but is permitted, a government may enact a voluntary standard to provide guidance to companies that choose to fortify all or a portion of their rice products. Once a national government legislates mandatory rice fortification, however, the accompanying standard becomes compulsory. All rice varieties that must be fortified according to the law must also adhere to the rice fortification standard. This includes domestically produced fortified rice, as well as fortified rice that is imported. It is best for countries to adopt the fortification standard as a legal document that is physically separate from the fortification legislation. You may be wondering why. At some point during the fortification program, stakeholders will decide to amend the standard to further the reach or the effectiveness of the initiative. It will be much easier to change a fortification standard that stands alone or accompanies other food fortification standards, compared to a standard that is embedded into the legislation. In most countries, altering legislation requires cooperation from multiple high-level entities in the government. Reaching an agreement takes time. On the other hand, a government technical agency often has the authority to amend food standards. The often emphasized specifications of a rice fortification standard include an explanation of what needs to be fortified, the micronutrients to be added, the amount of each micronutrient to be added, the micronutrient compounds to be used if applicable, the amounts of each micronutrient that must be present in fortified rice at the production point, or in the case of imported rice, at the border entry point. In many cases, the micronutrient levels are written as minimums. Ideally, however, each should be presented as a target value and range of variation. And lastly, the percent or amount of each micronutrient that must be retained after rinsing the fortified rice. The target value of each micronutrient listed in the fortification standard is formulated taking into account the following: the nutrient needs of the target population, and the average rice consumption among the target population. Though a population may consume multiple rice varieties, consumption patterns only need to be assessed for those that will be included in the rice fortification program. The acceptable range of variation, which accompanies the target value of each micronutrient, takes into account factors that can contribute to variable results when measuring micronutrient levels in rice. These include varying intrinsic levels of micronutrients in rice, variable distribution of added vitamins and minerals within the fortified rice, diverse dosing and blending capacities within a country's rice milling industry. In this hypothetical standard specification for total iron, 35 parts per million, or ppm, is the target value. 24 to 45 parts per million is the acceptable range of variation. The acceptable range, which accompanies the target level of each micronutrient, takes into account factors that can contribute to variations in the results of quantitative analyses measuring micronutrient levels. These include varying intrinsic levels of micronutrients in rice, variable distribution of added vitamins and minerals within the fortified rice, diverse dosing and blending capacities within a country's rice milling industry. In this hypothetical standard specification for total iron, 35 parts per million, or ppm, is the target level. 24 to 45 parts per million is the acceptable range. In 2009, the World Health Organization published recommendations on wheat and maize flour fortification. The recommendations for rice are currently in the development stage. Until WHO's recommendations for rice fortification are released, you may choose to use the chart presented here as guidance. A slightly different version was originally published as part of an article titled Proposing Nutrients and Nutrient Levels for Rice Fortification, which is available as a resource for this module. This newer version will be included in a book pending publication. Using the best available evidence, recommendations are presented for the 8 micronutrients that you see in the first column: iron, folic acid, vitamin B12, vitamin A, zinc, thiamine, niacin, and vitamin B6. Your country may choose to include all of those micronutrients, a portion thereof, or even additional micronutrients, depending on the nutritional needs of the population. As we saw previously in the course, one of the responsibilities of the multi-sector alliance might be to determine which micronutrients to include in fortified rice. For the 6 countries that have mandatory rice fortification programs, niacin and thiamine are the most commonly included vitamins, while iron is the most frequently used mineral. In fact, the Philippines only includes iron in its rice fortification standard. On the other hand, none of the other countries obligate rice millers to include vitamin A or vitamin B6. Perhaps you have noticed that riboflavin, also known as vitamin B2, hasn't been mentioned or shown, even though it is commonly included as an ingredient in premix used to fortify wheat and maize flour. The reason is that riboflavin is characterized by a bright yellow hue. At the high concentrations of riboflavin required for rice fortification, the kernels change color. Except for in a few niche markets, consumers reject such kernels and will pick them out before or after the rice is cooked. For this reason, certain nutrients and nutrient compounds are often considered inappropriate for rice. Here, you see a portion of Costa Rica's standard for rice fortification. The standard states that milled rice used for direct human consumption should be fortified with folic acid, thiamine, vitamin B12, niacin, vitamin E, selenium, and zinc. The figure to the right of each nutrient is the minimum amount that should be available in a kilogram of rice for regulatory purposes. The minimums include the intrinsic content of rice. In another chart, which isn't shown, the standard details the amount of each micronutrient that should be added to achieve the levels shown here. For example, the minimum requirement for thiamine is 6.0 milligrams per kilogram. To reach that, the other chart says that 5.3 milligrams per kilogram of thiamine must be added. This means that the typical intrinsic value of thiamine in rice is expected to be 0.7 milligrams per kilogram. Next up, we'll talk about vitamin and mineral blends and fortified kernels. I will sometimes refer to these collectively as fortification inputs throughout the course. When considering fortification inputs for rice, the first question to ask is, does the rice mill have an extruder or pasta press on site? If yes, the rice mill staff can order vitamin and mineral blends along with other necessary ingredients to produce fortified rice kernels. If no, the mill will need to source ready-made fortified kernels from a manufacturer. Fortificant blends and fortified kernels can be purchased locally if a manufacturer exists. This will largely depend on the demand for such ingredients in the country. However, in many cases, these inputs will be imported. High-quality vitamin and mineral blends are prepared with stable micronutrient compounds and are sold in durable packaging to promote protection from environmental hazards that could lead to contamination or micronutrient losses. Upon opening a package, the content should look uniform throughout. It is important that the micronutrients do not separate from one another during transport and storage. Finally, the vitamin and mineral blend should combine in a homogeneous manner with other ingredients used to produce the fortified kernels. The characteristics of fortified kernels are very similar to those of vitamin and mineral blends. However, fortified kernels should also look, cook, and taste like unfortified rice. Each rice mill should have a relationship with at least 2 relevant companies, either manufacturers of vitamin and mineral blends or manufacturers of fortified kernels. The potential for competitive pricing increases as more companies bid. Also, if one company has difficulties and cannot fulfill the order, the product can still be delivered by another company, avoiding a supply interruption. Manufacturers of fortification inputs must have access to a laboratory that tests each product batch for its content and quality. Results from such tests are listed on the product's certificate of analysis, a document that accompanies the shipment to the rice mill. We will talk more about certificates of analysis in the next module. Here is a list of fortified kernel producers from a rice fortification toolkit published by Gain and Path in 2015. The whole toolkit can be found in the Resources section of this module. For an up-to-date list, please contact the Food Fortification Initiative. Laboratories are an essential component of a comprehensive rice fortification monitoring system. First, I'll cover the 2 categories of analyses conducted by laboratories, followed by the various types of laboratories involved in a fortification program. 2 primary types of testing will be done by laboratories: qualitative and quantitative. Each test can be used independently, or they can be used in combination to reduce testing costs, as I will explain shortly. Qualitative testing determines only whether rice samples are fortified. The results will indicate yes, the rice is fortified, or no, the rice is not fortified. Have you ever heard of the iron spot test? It's the most common qualitative test used by millers and inspectors in countries that fortify flour to detect the presence of iron fortificants. It can also be adapted for use with rice. All iron compounds used to fortify rice are in their ferric form, so only 2 reagents are needed. Please note, this methodology differs from testing wheat and maize flour. To conduct the iron spot test, solutions must be made from the reagents. These are then added to a sample of rice consecutively. After a few minutes, fortified kernels will turn dark red. Directions for the iron spot test are available in the Resources section of this module. This topic will be expanded upon with visuals in the Internal Monitoring module. Qualitative tests, such as the iron spot test, are conducted by both millers and regulatory authorities. The iron spot test can, but does not have to be, conducted inside a laboratory setting. Quantitative analyses determine the micronutrient levels in a sample of fortified rice. Often, the quantity of only 1 to 2 marker nutrients, such as iron and folic acid, are determined, because comprehensive testing can be expensive. The term marker micronutrients is used for the following reason. Assuming a reputable company produced the vitamin and mineral blend, or the fortified kernels, one can assume that the micronutrient levels are proportionate. With that in mind, if the quantity of iron in a fortified rice sample is compliant with the specifications of the fortification standard, the results of the other fortificants are expected to be as well. For quantitative analyses, composite samples are generally utilized. They are comprised of at least 3 single samples of rice. Analysis of composite samples saves time and resources by reducing the analytical burden on laboratories. Also, given the small micronutrient quantities added to fortified rice, having a composite, and thus a larger sample from which to test, also increases the accuracy of the quantitative results. Analysis of folic acid is usually done with a method called liquid chromatography mass spectrometry. Iron is usually measured using atomic absorption spectroscopy. Details about quantitative methods for measuring folic acid, iron, and other micronutrients in flour are available in the Resources section of this module. These can be adapted for rice. Prior to conducting an analysis, rice samples should be ground, then mixed. Only then should laboratory staff extract the aliquot for testing purposes. As noted earlier, qualitative and quantitative analyses can be used in combination to reduce testing costs. For example, a government inspector takes 5 single samples of rice from a mill warehouse during an inspection visit. An iron spot test determines that all are fortified. A composite sample is then created using the remaining portion of each single sample. The composite sample is sent to the government laboratory to undergo quantitative analyses. It is less expensive to run the analyses on one composite sample than 5 single samples. Now that we have finished our overview of the testing methods, let's move on to the topic of types of laboratories. Fortification programs involved multiple types of laboratories as indicated in this diagram. Starting at the bottom, some companies that manufacture vitamin and mineral blends and fortified kernels have their own laboratories. However, when they need to verify product quality, they generally send samples to an independent third-party laboratory. The other types of laboratories, which we will cover in more detail in a minute, include mill laboratories, central mill laboratories, government laboratories, reference laboratories, and independent third-party laboratories. Many modern mills have laboratories. Assuming that's the case, the quality control manager may be responsible for collecting rice samples, conducting iron spot tests, checking the fortified rice kernel feed rate, and sending composite samples to technologically advanced laboratories for quantitative analysis. If a company owns multiple rice mills within a country or region, it might support a central laboratory. Representatives from this laboratory will audit the practices of the individual mills within the company. Some are also able to run quantitative analyses on samples of rice. However, that capacity is not essential for 3 reasons. First, the equipment to quantitatively measure micronutrients can be expensive, depending on the micronutrient to be analyzed. Second, implementation of a strong quality management system at the rice mill naturally facilitates proper rice fortification without regular quantitative testing. And third, results from an independent third-party laboratory are viewed more favorably by government inspectors and clients. The primary role of government laboratories is to run qualitative and quantitative tests on samples of fortified rice or fortification inputs. In the case of external and import monitoring, the government laboratory will generally receive composite samples of fortified rice that were collected by inspectors from rice mills or border control sites. Lab technicians test these quantitatively for at least one marker nutrient. In the case of commercial monitoring, the government laboratory will generally test single rice samples qualitatively first, then form composite samples as directed by the legislative documents for the fortification program. Each composite sample then undergoes quantitative testing. If fortification inputs are imported, samples of fortificant blends and fortified kernels are periodically collected at the border and sent for quantitative analysis as well. Reference laboratories may be available within a country, but in some instances, they are regionally based. Oftentimes, government laboratories only have the capacity to analyze 1 or 2 micronutrients, but reference laboratories should be able to analyze a variety of micronutrients in samples of both rice and fortification inputs. These laboratories may serve as a reference and quality assurance check for other types of laboratories. Additionally, the laboratories may verify the quantitative results of fortified rice samples if a dispute arises between a government laboratory and a rice mill. Independent, third-party laboratories may be available within a country or a region. They are usually privately owned. Their main function is to be available to test the quantity of any micronutrients that must be added to rice according to the fortification standard. They should be able to conduct these tests on rice and fortification inputs. As mentioned earlier, manufacturers of fortification inputs may seek out third-party laboratories to verify that product batches contain what the customer ordered at the appropriate levels. Optimally, a laboratory that conducts quantitative assessments for the rice fortification program should have the capacity to analyze all micronutrients of interest, be ISO 17025 certified to measure the micronutrients of interest in rice or fortification inputs, have proper storage conditions for all types of samples and for chemicals used in the analyses, be able to analyze samples and distribute results in a timely manner. As a reminder, ISO stands for the International Organization for Standardization. Laboratories that have ISO 17025 have demonstrated that they are able to produce precise and accurate test and/or calibration data. To recap what we've covered in the course so far, you've learned about the importance of food fortification, the types of rice fortification methods implemented around the world, the role of a multi-sector alliance in a country's fortification program, how to plan for fortification monitoring, standards, fortification inputs, and laboratories. With these foundational modules completed, we will move into the heart of the course: internal and regulatory monitoring.